11.5. The motion of gyroscopes and tops. The outline of this video is as follows. First, we will introduce the concept of precessional motion, which is the slow rotation of the axis of a spinning object. We will use the familiar example of a spinning top to build our intuition. Next, we will analyze the forces acting on a gyroscope, specifically gravity, and see how these forces produce a torque. This torque is the key to understanding why the gyroscope's axis moves in the first place. Finally, we will connect the concepts of torque and angular momentum to derive an equation for the precessional frequency. This equation will allow us to calculate how quickly the axis of the spinning object precesses. Let us begin by exploring the fascinating motion of a rapidly spinning object, like a toy top or a gyroscope. When you spin a top, you will notice that its main axis of rotation does not stay fixed in one direction. Instead, this axis slowly rotates around a vertical line, sweeping out the shape of a cone. This slow secondary rotation of the main spin axis is what we call precessional motion. This behavior brings up a very natural question. Why does the top do this instead of just falling over? Its center of mass is not directly above the pivot point, so gravity is certainly creating a torque that should topple it. The answer lies in the interaction between this gravitational torque and the top's large angular momentum, which it has because of its fast spin. To understand why a spinning top precesses instead of falling, we must analyze how torque changes the angular momentum vector over time. To understand why a gyroscope precesses instead of simply falling over, we must first identify the forces acting on it and the net torque they produce. There are two main forces to consider. The first is the force of gravity, which acts downward at the gyroscope's center of mass. The second is the upward normal force exerted by the pivot point that supports the gyroscope. Let us analyze the torque produced by each force about the pivot point. Because the normal force acts directly at the pivot, its moment arm is zero, and therefore it produces zero torque. The gravitational force, however, acts at a distance from the pivot. This force creates a non-zero torque, which is calculated as the cross product of the position vector r and the gravitational force mg. Using the right-hand rule, we find this torque vector is directed horizontally. It is perpendicular to both the tilted axis of the gyroscope and the downward force of gravity. The key takeaway is that a tilted gyroscope experiences a net horizontal torque due to gravity. Now let us connect torque and angular momentum to explain why a gyroscope precesses instead of falling over. The key physical principle is that the net external torque is equal to the time rate of change of angular momentum. In equation form, this is tau equals the quantity dl over dt. This relationship tells us that an applied torque causes the angular momentum to change over a small time interval. Most importantly, the direction of this small change, which we call dl, is exactly the same as the direction of the torque. For our gyroscope, the torque from gravity is horizontal and perpendicular to the angular momentum vector L. Therefore, the change dl must also be horizontal and perpendicular to L. When you add a small vector dl at a right angle to a large vector L, the result is a new vector that has nearly the same magnitude but is pointing in a slightly different direction. This continuous change in direction, driven by the torque, is precession. The key takeaway is that a torque perpendicular to the angular momentum causes the direction of the angular momentum to rotate, not its magnitude to change. We can now quantify the precessional motion by deriving an expression for the small angle that the angular momentum vector rotates through. Looking at the vector geometry, for a very small time interval, the angular momentum vector L rotates through a small angle, which we call d phi. This angle can be approximated by the fraction of the magnitude of the change, dl, over the magnitude of the original angular momentum, L. To find dl, we recall that the change in angular momentum is equal to the torque multiplied by the time interval, dt. The torque here is caused by gravity, and its magnitude is the force, m times g times the lever arm, which is the distance, r sub cm from the pivot to the center of mass. By substituting these expressions into our equation for the angle, we get a direct relationship. The angle of precession, d phi, is equal to the quantity m times g times r sub cm all over L, multiplied by the time interval dt. This result sets the stage for finding the precessional frequency. We can now define the rate at which the gyroscope's axis rotates. This quantity is called the precessional frequency, represented by the Greek letter omega with a subscript, p. It is defined as the time rate of change of the angle phi, or d phi over dt. Using the relationship we found on the previous slide, this frequency is equal to the quantity mgr sub cm, divided by the magnitude of the angular momentum L. We also know that the angular momentum L is the product of the moment of inertia I and the spin speed omega. Substituting this into our equation gives the final expression. The precessional frequency omega sub p is equal to mgr sub cm, divided by the quantity I times omega. This result is a very useful approximation, but it is only valid when the precessional speed is much, much smaller than the spin speed. This is generally true when the gyroscope is spinning very rapidly. A key insight from this equation is that a faster spin speed results in a slower precessional frequency. Let us summarize the key principles that explain the precessional motion of a gyroscope. The entire process begins with the force of gravity, which acts on the object's center of mass. Because the top is tilted, this force creates a torque about the pivot point. Crucially, this gravitational torque vector is always perpendicular to the gyroscope's angular momentum vector, which points along the spin axis. Now remember that a torque causes a change in angular momentum. Because the torque is perpendicular, it does not change how fast the top is spinning. Instead, it only changes the direction of the angular momentum vector. This continuous redirection of the spin axis is exactly what precession is. The rate of this precession, or the precessional frequency omega sub p, is given by the equation omega sub p equals the quantity m times g times r sub cm, all divided by I times omega. This leads to the most important takeaway. The faster the gyroscope spins, which means omega is large, the more slowly it precesses, meaning omega sub p will be small. Let us work through these two review questions to apply our understanding of precessions. For the first question, we connect the direction of precession to the direction of the angular momentum vector. The torque from gravity is what causes the change in angular momentum, dl. For the gyroscope to precess counterclockwise when viewed from above, the change vector dl must point tangentially in that direction. If you visualize adding this change to the main angular momentum vector L, you will find this only works if L is pointing generally upwards along the axis. If L were pointing downwards, the same exact torque would cause a clockwise precession. The second question tests the relationship between spin speed and precessional frequency. The formula we derived shows that precessional frequency is inversely proportional to the spin angular speed. Since the mass and dimensions of the top are the same, all other factors are constant. Therefore, if the new top spins at twice the speed, its precessional frequency will be cut in half. This is a key insight. Spinning a top faster makes it precess more slowly and thus appear more stable.